So welcome to the video on detailing one-way slabs. So a one-way slab looks like this, right? That's what we were discussing in the previous slides. This is a parquet structure, and then we know that the load is moving predominantly in this direction, right? That's why it's called a one-way slab. So the first step is to find the minimum slab thickness to meet deflection requirements, and we know that if we follow what table 9.2 says, right, we don't have to worry about deflections, right? Although that's likely to share in new versions of the code, but we don't have to worry about that now, right? The second step is to find the design moments and shears, right? We check if approximate values apply first, right? And this is what we are going to discuss in a little bit, right? And then what is contained in the manual for moments and shear in continuous elements that you have, right? Otherwise, we use a different method, namely a computer method, right? There are many software packages that do this for us, right? Finding moments and shears for continuous members. We find minimum cover requirements according to the use and the environment at which this one-way slab is going to be subjected, right? And we choose the bar depth, right? The location of the bar, right? Finally, we choose bar cutoff locations, right? Bar cutoff locations, we remember it was quite an interesting process. Fortunately, there is a simplified method to do it, to do here, right? The fifth step, right, is actually choose the amount of reinforcement we need, right, for temperature and shrinkage, right, that's to prevent cracking and other long-term deformations, maximum and minimum reinforcement spacing, right, and then importantly, right, how much steel you need for strength, right, so that you can provide enough moment resistance, right, compared to the factor moment. Then we do the reinforcement in the transverse direction, right, for shrinkage and temperature control. We check cracking, right, it's very similar to doing the one that we did for a beam, and then check shear, right. It rarely governs the span. The span of these one-way slabs is actually way larger than we have to be worried about the shear. For example, in a long member, right, or any member, right, the moment is WL squared divided by 8, right, and then the shear is simply WL over 2, right? So in this moment diagram, right, the moment is increasing with the square of the length, and in the shear diagram, the shear is increasing with only the just the first power of L, right? So the moment is increasing more in as you increase the length, right? So in longer elements, right, the moment is going to be usually more of a concern than the shear, right? So let's go to the steps, right? Let's go to the steps. Do you remember what was the first step, right? Choose the slab thickness, and then we have table 9.2 in which we used to select the thickness of our element, so we don't have to worry about a detailed deflection later. So in this case, right, we have our one-way slabs here, right? One-way slabs here, right? Or ribbed one-way slabs, right? So it could be the sort of system that that we may have, right? We will see in a minute how they look like, right? A flat or solid and ribbed slabs, right? Well, sneak peek, right? Let's go to the next slide, and you take a look at what is a solid and ribbed slab, right? So that's how they look. So depending on which sort of slab you have, right? If it's simply supported, right? These are values of minimum thickness you can have, right? One end continuous, right, and the other is simply supported, of course. What about the span, right, that is has both end continuous, and what about the one-way slab that acts as a cantilever, right? So those are the minimum thickness in table 9.2 that you could use. If you have several spans, several spans, we don't, and the spans may have different lengths, right? And you see that these thicknesses here in this table they depend on the clear span, Ln, right? Ln is a clear span. So in the case that you have different clear spans, and then you are going to have different thicknesses in each span, right? We usually don't change the thickness of a slab from span to span, right? We typically use the same thickness across all the spans, so you'll be choosing the one that controls, right? The thickest dimension you get, that's the one that you would use on your design, right? So ribbed slabs, right, and flat slabs, right, and flat slabs, and that is what you would have, right? What you would have. So slab thickness notes, right? Select the thickness in 10 millimeter increments. In practice, 10, 20, and 25 millimeter thickness increments are used, right, depending on the project, right? So design, if you design a thinner slab, right, not following table 9.2, it's allowed, right? It's allowed. You can design them, but then you will need to do a detailed deflection check, which is outside of the 474 scope for the one-way slab, right? Now, if the slab is connected to elements that are likely to be damaged by large deflections, you cannot use table 9.2, right? Because you would have some amount of deflections, right? The code only says that you don't have to worry about them; they wouldn't compromise the safety of it, but you would have deflection, right? So you'll have to keep that in mind, right? If you want to absolutely your deflections because you have sensitive equipment connected to your one-way slab, then you definitely need to use a different method. After you have chosen the thickness, right, you will know the self-weight, and then you are in a position to calculate moment and shear coefficients, right? So this is the material you were given before, right, in which we use tables to define the moment and shear coefficients, right? You have to check that you can use them, right? That this simplified method applies, right? And then, just as a brief reminder, right? You have to use different methods if you cannot, right? But if you can, right? If you have a regular frame, right? These are the diagrams that will allow you to calculate moments for two span structures. Right? Take a look. We have here in a summarized way what the moments look like and what the shear forces look like in continuous structures. Right? Take a look at the fact that the moment diagrams are inverted. Right? In this case, right? Diagrams are inverted. Now this is for two span structures, right? And if you have more than two spans, right, you can use these diagrams, right? Take a look at where you are in your structure, and then that's how you could identify what the moments and shear forces are, right? These moments and shears are in terms of the factor load and the clear span, right? The clear span of your structures. Clear span, right? Clear span is this dimension, right? This is a clear span, right? This is the clear span that we refer to in this table, right? So once you have found the moments and the shears, right, you're going to do the cover requirements, right? Cover requirements, right, is the same table that we had from before, right? And then we are going to be now focusing on slabs, right? And slabs that are here for normal exposure, right? And then the freeze and thaw, right? The freeze and thaw category, right? The chloride categories, right? That we have here. So depending on that, those categories of exposure, you would select your clear cover, right? So the minimum clear cover you can provide, right, in a exposure class M, right, which is typical for one-way slabs in buildings, will be the greatest of 20 mils right? That's a complete table that we had before. Diameter of the bar closest to the slab surface, 1.5 AG, right? This is for top bars, right? On a screeded surface, right? So what is screeding, right, of a slab? And 1.0 times AG for a bottom bar, right? If you have a formed surface. Well, screeded, right, is the fact that you have you're going to have a bit. Well, this is usually the top of a slab, right? You pour the concrete, and then the top surface has to be right. You have several tools that you want to make it flat, right? So you pass a right in the concrete surface. You pass a piece of wood, right, or a different tool, right? You pass it, right, one time, right, over your concrete, and then another, right, just trying to flatten it, right, just to eliminate any bumps, right? Sometimes they aggregate, right, the small pieces of rock, right, are going to get trapped into this piece that you're moving side by side, right, just trying to flatten. And then those small gravelly pieces, right, are going to create small bumps, right? You remove this, and then you end up having a bump or a small valley on your screeded surface, right? So sometimes, right, that bump or that valley, right, the valley gets too close to one of the rivers, right? So that is why for top bars in screeded surfaces, right, anticipating the fact that you may have a valley close to a river, you're going to have to increase the clear cover, right? You don't have to have that requirement for the bottom of the slab, because this has a nice flat form, right? So there is no possibility of having a valley or getting a valley there, right? So one more thing about clear cover, right? One more thing about clear cover. This table 17 that we just saw, right, is reasonable for protecting reinforcement from corrosion, right, and allows concrete to be placed with good, right. It's going to be easy for you to pour the concrete around the reinforcement, right? But more cover may be needed to achieve the desired fire rating for the element, right? Now, fire ratings are going to be outside of the 474 scope, but be aware that that fire ratings may actually govern, right? May actually govern the design, right? So always be aware of what you are being tasked to design, right? So what does the reinforcement layout looks like for one-way slabs, right, in continuous members? Well, we have our bottom steel, right, for positive moment resistance, right? We have top bars for negative moment resistance, right, where we have negative moments, which is beam and column locations, right? We are going to hook the reinforcement at the exterior column and beam, right? And then these transverse bars, right, going in the other way as the load sharing, right? They're going to be the bars for shrinkage and temperature. So it's a good reminder of how our reinforcement is going to look like. Now, if we know where our reinforcement is going to be, right, let's talk about cutoffs, right? And then you may, right, there are only two types of people in the world, right? People who hate cutoffs and people who hate cutoffs, right? Then, right? No, we are not going to go through all the process. It's not that it's not interesting, right? It's quite interesting, but we're not going to go through the process of how to cut rebars due to flexion and shear and development, right? So if you follow, right, these requirements, you can avoid doing that, right? So what are the generic cutoff requirements, right? Standard hooks, right? Standard hooks for the intersection with the outer column, right? Minimum of 150 mils typical penetration of the positive reinforcement into the support, right? Clear span over 4, right, in the outer span, right? Larger span, right? Larger length of clear span divided by 3 for each of the 3 spans, right? That's for the negative reinforcement, right? Take a look at the penetration here, right? 150 mils, right? And then, right, the negative reinforcement larger of span over 3, right? According to to the span that you may have, right? So easy requirements, right? Easy requirements to follow, right? You have to check just that that the conditions are met, right? So generic cutoff locations give conservative results for one-way slabs, provided you satisfy approximate frame conditions, and we'll get to see what those frame conditions are, right? They are also on the previous handout, previous set. If you do not meet the approximate frame conditions, again, we are going to go over them again, or you want to be more detailed, right? You could design, of course, right, cutoffs using the principles shown in the previous lecture, right? If you want, if you want. Now, notice that all the reinforcement splices are required to develop their full yield strength, right? This is because we're designing what essentially amounts to a beam. So in beam, you remember, we wanted the steel to yield, right? So if we want the steel to yield, right, there is not going to be reduction factors due to AS provided over AS required, right? Given in this particular case. If you remember, we were allowed to reduce our development length if we had more steel than needed, but in this case, as we want the steel to yield, there is not going to be such reduction, right? Such reduction. So how do we define our steel, right? So usually, right, our one-way slabs are going to be designed as 1 meter wide elements, right? So B is equal to 1,000 mils. It doesn't mean that that's just the width of the beam, kind of a slab, right? No, it's just the width of our design strip. So since we're going to provide the steel per meter, right? That's how we're going to define it. The slab reinforcement is going to be typically given, right, in units of square millimeters over meter, right? Because it's area of steel per meter, right? So we get that unit, right, by taking the area of 1 bar in square mils and divided by the center to center bar spacing, right? Bar spacing. So how does that look like, right? So 115 bar at 400 millimeter spacing, right, which is very typical to see on a drawing. So how does that look like, right? How many square mils per meter? Well, it's just a simple proportion, right? A 15 millimeter 15 bar is 200 square mils. So 200 square mils at 400 millimeter spacing. How much of it per 1,000 millimeter spacing? And then we obtain that 115 bar at 400 millimeter spacing is equivalent to say that there is 500 square mils per meter, right? That is what it is. And then we can go back and forth from this calculation, right? So because we're going to get our steel, right, later on, when we calculate how much steel you need to carry in a moment, you're going to get it in square mils per meter. And then you are going to have to convert that into how many bars and at what spacing. So that's why how you convert that, right? What type of steel we need, right? Well, depends on 3 requirements, right? Temperature and shrinkage requirements, maximum bar spacing requirements, and also strength the strength requirements, of course, right? So what about temperature and shrinkage, right? So we saw, well, there are some deformations caused by temperature and shrinkage, but how does that work? So as concrete cures, right, the chemical reaction in which the concrete, the cementitious product attain the strength in reinforced concrete, right? That reaction, right, is going to use up all the water, and then the concrete is going to dehydrate, right? So as concrete cures, it shrinks, right? And then concrete also expands and contracts as temperature changes, right? So concrete is going to be contracting and expanding, right? Contracting due to shrinkage, right? Expanding if there are hot temperatures, contracting if there is cold, right? So for example, right, let's get a sense of how much. So a 10 meter long member will expand or contract 1 mil when temperature changes by 10 degrees Celsius, right? So does not sound like much, but these effects can be significant enough to cause cracking, right? To cause cracking. It's quite quite typical to see these cracks, right? Now, temperature changes can occur during construction of interior exposure slabs, right? So even those that are inside buildings are susceptible to this cracking, right? Now, if you have a simply supported beam, right, and this is a quite interesting effect. If you had a simply supported beam, right, let's say it contracts because it gets cold, right? There is not going to be any cracking in this case, right? Because that beam is going to be able to roll, right, to the new length quite easily, right? The fact that it doesn't crack doesn't mean that we are off, right? Like we don't have any problem, right? Imagine a concrete beam in a bridge, right? Well, if you may have noticed, right, there are these kind of teeth onto the ends of bridges, right? Sometimes in the middle of bridges, right? If you have right supports in a bridge, right? So you see this teeth here, right? So those teeth are protecting your beam, right? Because it's rolling and maybe getting shorter, right? When it gets shorter, you create spaces here, right? But these teeth allow the car to still pass through that gap, right? That gap. So it's quite interesting. So these are some of the expansion joints, right? So quite typical in bridges. So next time you go by whatever concrete bridge, right, take a look. They will have expansion joints such as this one. Well, this is the beam can it's simply supported, right? Just rolls to the new length. What if you fixed it, right? And then in some applications you have to have a fixed condition. Now, when it tries to contract, right, it cannot, right? So it will crack, right? So supports will introduce these effects that you have to consider, right? So the beam will want to shrink by a length delta, right? The length delta is the 1 millimeter per 10 degrees Celsius, right? But it cannot, right? This restraint causes tension. If you want to calculate the tension force that this deformation will cause, right? In terms of axial stiffness, right? This is how you can calculate the tensile stress. Now, if you reach 0.6 square root of ft, right? Remember that's the tensile strength of concrete. You're going to crack it, right? So no loads on the beam, but you will still crack it due to temperature effects. So to prevent temperature effects, right? Your slab must contain steel, right, with an area of at least 0.002 times the gross section area, right? So you're going to be requiring these temperature and shrinkage requirements. You're going to be defining or checking it for the two directions, right? For the two directions of the slab. So this is my one-way slab. This is the 1 meter design strip. So I have to check this requirement in this direction and also in this direction. Right? Not that it's a two-way slab. You have to protect it against these temperature and shrinkage requirements in both directions, right? So okay, so you let's say for this direction, you end up needing some steel transversely, right, like this, and then you do the check for the main load direction, and then you end up with whatever amount of steel, let's say 200 square mils per meter, right? And then for strength you require 500 square mils per meter. And they say, oh, do I need now 700? No, you are allowed to, right? You are allowed to use your flexural steel, right, as also temperature and shrinkage requirement, right? So that's how you're going to think about the two requirements together, right? So 0.002 times Ag to address temperature and shrinkage concerns. Ag is the gross slab area for 1 meter for a 1 meter wide slab, right? The gross section area is the thickness of the slab times 1,000 mils, right? and then knowing that both top and bottom steel reinforcement will count as temperature in shrinkage requirements, right? Now, just a note, right? You can waive this limit if the resisting moment is bigger than 1.33 times the factor moment, because this means that you are going to have excess reinforcement, right? If you're providing enough moment that you are 30% over the factor moment, it's assumed that you will have enough for temperature and shrinkage requirements. What about bar spacing requirements, right? What is the minimum bar spacing requirements? This rarely control, right? But it's the same as we had for beams: 1.4 times dB, 1.4 times the aggregate size in 30 mils, right? Is the list of them. It's the same limit that we use for beams, right? Rarely controlled. We rarely have this requirements control. You'll see that the spacings of my bar will be on the order of 200, 300, 400, 500 millimeters, right? So it's very rarely a concern, right? It's very rarely a concern. Usually it's not even checked, right? Now, the recommendation is that you have to check the minimum spacing if the bar center to center is less than 75 mils. But if you have to have reinforcement in a one-way slab in which you need bars at less than 75 or 75 mils or around 75 mils, there is something else going on that beam. There is too much load, right? There is too much load. What about the maximum requirements, right? You don't want to get your bars spaced too far apart. Well, that may control, right? That may control the maximum spacing, right? You may when you finish calculating your steel, you may find that you need bars at 700, like very widely spaced, 700 mils. Well, no, that's not allowed, right? So for principal, right, moment resisting longitudinal steel, the maximum bar spacing is the least of 3 times the thickness, right, of the slab, or 500 mils, right? Whichever is less, right? Whichever is less. And this is just protecting you from situations in which you have loads that surprise you between bars, right? No, you don't want that, right? You may punch a hole through the slab. So you want these bars to be close enough. So these are some of the detailing requirements in the code. So how to choose a steel, how to place it. What about transverse steel that you need for temperature and shrinkage, right? And then in the next video, right, we will be talking about how to calculate the steel, in our one-way slab systems. Thank you very much, and see you in the next video.